All right, 2.5 are about radical, or 0.6 is about radical functions. So we're going to spend some time just kind of reacquainting ourselves with radicals and radical notation in this section. And then we'll talk about how to graph and solve equations involving radicals and things like that. So first of all, recall that this symbol here, if you say, we read this the mth root of a. So if you have a statement that says mth root of a equals b, what that means is that b to the mth power equals a. So for example, the cubed root of 8 is 2 because 2 cubed equals 8, right? Okay. And when there's not an index written, so this number in here inside of the little radical sign is called the index. When there's not a written index, it's assumed to be a square root. So square root of 25 is 5 because 5 squared is 25. Okay. So this is a radical. We assume it to be a 2. A is called the radicand. Okay, so those are just some pieces of vocabulary that might come in handy as we discuss these things. Give the video a pause and see if you can work out these 8 problems to see if you got the handle on radicals. Okay, here are my solutions. Square root of 64 is 8. Square root of negative 64 is 8i, right? Cube root of 64 is 4. Cube root of negative 64. If you wrote 4i, your heart was in the right side. Think about it, right? Negative 4 times negative 4 is positive 16. So you don't need to call it 4i or negative 4i or something like that. It's just negative 4. In general, there's no problem with taking odd index radicals of negative numbers, right? That's not an issue. It's only when you have even index radicals of negative numbers that you need to, that the solutions to those are not real numbers, right? Anyway, cube root of 3 cubed is 3, right? Because 3 cubed is 27, cube root of 27 is 3. Cube root of negative 3 cubed is negative 3, right? Negative 3 cubed is negative 27. And cube root of negative 27 is negative 3. 3 to the fourth is 3. 3 to the fourth is 81, right? And fourth root of 81 is 3. But fourth root of negative 3 to the fourth is also positive 3. It's kind of this weird thing, right? But if you think about it, negative 3 to the fourth power would be positive 81, and then the fourth root of positive 81 is positive 3. So just be careful. Basically, if we wanted to summarize like all of our discoveries here, we could come up with a whole list of properties that we could talk about with radicals, especially when they involve negative radicands. But generally speaking, rather than memorize a bunch of rules, we're just going to be careful and we're just going to think things through. I think if we do that, it'll work out better for us than if we try to memorize a whole bunch of rules about when your answer is positive, when the answer is negative, when the answer needs an I on it, and so forth. It's much better to just think about it. Just think about it. Okay? However, there are 3 rules that will come in handy, and they're these 3. So this first one I call the product rule. Second one I call the quotient rule. And the product and quotient rules are all about how radicals distribute across multiplication and division, right? Distribute across addition and subtraction. So be careful, right? Square root of a plus b is not the same thing as square root of a plus square root of b. But they distribute across multiplication and division. And then the other thing is when you have exponents and radicals, the way that they interact is that the order doesn't matter. You can use the nth root, or you can take the nth root of a and then raise that to the nth power, right? You're going to get the same answer either way. There are some slight details where that's not true, but as long as we're thinking these things through carefully, we're not going to run into any kinds of issues. So let's practice simplifying some stuff. Square root of 4x, for example. We could think of this as square root 4 times square root x. And square root 4, of course, is 2. So this is really 2 root x. It's another way to say the same thing. Cube root 24 x to the 4th. Same idea, right? Cube root 24. Well, what we could do is we could think of this like, what's the largest perfect cube that goes into 24? And to think about that, you kind of have to have a list of perfect cubes in your mind, right? So 1 cube. So already, when we get to 3 cubed, we've gone too far. But 8 does go into 24, right? So we can think of this as times. 8 times 3 is 24, so we have a 3 left over and then an extra x left over. And then the product rule tells us this is just going to be cube root of 8x cubed times cube root of 3x. And then the cube root of 8x cubed is just 2x. So there's the simplified version of what we started with there. I may not show so many steps, right, when I do this, generally speaking, but that's kind of how this works. When you're multiplying two radicals, you multiply the coefficients and you multiply the radicands. So in this case, we would get 5 times 7 is 35. And inside the square root, 6 is 60. Of course, you can simplify that, right? You should think of the largest, in this case, since root, you should think of the largest perfect square that goes into 60. Squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and then by the time we get to 8 squared, we've already gone too far. So is there any number on this list? And if so, what's the largest number on this list that goes into 60 evenly? And the answer, I think, is 4. 4 is the best we can do. We can rewrite this as 35. 60 is 4 times 15. And square root of 4 is 2. So this is 35 times 2, root 15. That's 70. 70 root 15. Okay? Cube root 72. We need to think of the largest perfect cube that goes into 72. Here we started making lists of perfect cubes. 1, 8, 27. 8 goes into 72. Let's see if there's something bigger, right? Does 27 go into 72? No. What's the next one? 4 cubed is 64. I don't think 64 goes into 72. And 5 cubed is 125. 125 definitely does. So I think 8 is the biggest, right? This is going to be cube root of 8 times 9. That's 2 times the cube root of 9. Fourth root of 48, a to the 11th, b to the 12th, c to the 5th. So something that, if you've worked with radicals in the past, then something that you may have caught on to was the idea that if you have these large exponents in here, really what you can do is you can divide these exponents by the index. And the quotient goes on the outside, the remainder stays on the inside of the radical, okay? So as it relates to a to the 11th, b to the 12th, c to the 5th, now the 48 we'll have to take care of kind of separately, but just as far as the variables are concerned, I can think of 11 divided by 4. How many times does 4 go into 11? Well, it goes in twice, right? So I'm going to have an a squared on the outside of the radical. And then on the inside of the radical, how many do I have left over, right? 4 goes into 11 twice with 3 left over. So I'm going to have an a cubed left over. With b to the 12th, 4 goes into 12 3 times. with no leftovers. So I'm not going to have any b's left over on the inside of the radical. And then c to the fifth, right? 4 goes into 4 goes into 5 once. So I'm going to have a c to the first power on the outside, and then with 1 left over. So I'm going to have a c to the first power on the inside. What about that 48, though? The 48, I have to think of the largest perfect fourth that goes into 48. So let's make a list of perfect fourths, right? 1 to the fourth is 1. 2 to the fourth is 16. 16 goes into 48. Let's see if there's a bigger one. 3 to the fourth. 3 times 3 is 9, times 3 is 27, times 3 is 81. That's already too big, right? So 16. 16 goes into 48 3 times, right? 16 times 3 is 48. Well, what's the fourth root of 16? It's 2. And then we have the 3 left over on the inside, right? So we have, right, 16 times 3. So we have I put cube root, but that should be a fourth root. I apologize. So we have 16 times 3, right? Fourth root of 16 is 2. Anyway, so that's that one. Just like with everything else I show you in this class, if you don't like the way I do it another way. It doesn't bother me. Feel free to do it some other way. I'm just trying to refresh your memory. This is something that you should know how to do already from your past experience in algebra. So if you like it a different way, feel free to do it a different way. But you should be able to end up here. Okay, you'll have plenty of opportunities to practice this in the homework. Let's do part F. So I multiply these two things. Now they have the same radicand, so the product rule applies here. So I can go ahead and say this is just going to be the fourth root of a to the 8th, right? A to the third times a to the fifth is a to the 3 plus 5, right? A to the 8th. Now what's the fourth root of a to the 8th? That should just be a squared. Okay, so that's that. So on the previous page, I mean, we kind of saw some ways that we can add, or some ways that we can multiply and divide radical. Well, we didn't look at division so much. We mainly looked at simplifying and multiplying radical expressions. Let's talk about adding and subtracting, though. And then we'll talk about division. We'll talk about division down here. Let's talk about adding and subtracting. So, two radicals with the same radicand and same index are called like radicals, and only like radicals can be added or subtracted. To do so, we treat them like variables, right? That is to say, we add the coefficients and then we leave the radical unchanged. Now, the problem is when you're dealing with something like part A, it seems like they're not like radicals because you've got square root of 12, square root of 3. The radicands don't match, so they're not like radicals. But the thing is, you can simplify the square root of 12, right? There's a perfect square that goes into 12, and it's 4, right? 4 goes into 12. So we can think of the square root of 12 is really 4 times 3. Square root of 4 is 2. So this is 2 root 3. So 12 is really the same thing as 2 root 3. Okay, 3 times 2 is 6. So we have 6 root 3 plus 7 root 3. And there you go, right? Now they're like radicals. This isn't always possible, but it just so happens in this case that 12 reduces to, the square root of 12 reduces to 2 root 3. Okay, and now to combine these terms, we just add the coefficients. 6 plus 7 is 13. So our final answer is 13 root 3. We can do the same thing for something slightly more complicated looking, like part B. So we're dealing with cube roots now. With the 135, I should be thinking of the largest perfect cube that goes into 135. So a list of perfect cubes again is something like 8, 1, 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and that's already getting too big to do anything with. But I know that 8 goes into 40. I'm curious to know, maybe does 8 go into 135? Let me see. 135 divided by 8. No. What about 27? 135 divided by 27. Yes. 27 goes in 5 times. So let me rewrite this kind of in the long way. This is going to be 2 times the cube root of 27 times 5x minus 3 times the cube root of 8 times 5x. Cube root of 27 is 3, so this is 2 times 3 times the cube root of 5x minus 3 times cube root of 8 is 2, so it's 2 times the cube root of 5x. So we've got, look at that, we've got 6 cube root 5x minus 6 cube root 5x. Well, that's 0. So what do you know? This thing right here is just a fancy way of saying 0. That's why we like to be able to simplify, you know? It's nice to know that this weird thing is just really 0. Okay? So that's that. That's how we can add and subtract. Let's talk about division. When we're dividing with radicals, really what we end up wanting to do is we want to rationalize the denominator. And what that means is we want to rewrite the expression so that there are no radicals in the denominator and so that there are no fractions in your radicand. So part A, for example, is a problem because we've got a radical in the denominator. We undo that by multiplying by something that will clear the radical. In this case, I've got square root of 8. I could multiply by the square root of 8, and then I would get the square root of 64. The square root of 64 is just 8, and so then the radical would cancel. That would work. You would have some simplifying you would have to do at the end of that problem, though. So if you want to avoid having to do so much simplification, you could look for the smallest thing. Instead of just multiplying by this exact expression, you could look for the smallest thing that'll do the trick. Like in this case, I know that if I multiply by the square root of 2, 8 times 2 is 16, and 16 is a perfect square, right? So if I multiply by the square root of 2, I'll get the square root of 16, which is just 4. And then I won't have any simplifying that I have to do, right? So I'm going to get 7 root 2 over root 16. That's 7 root 2 over 4. Okay? And even though this looks more complicated than that, this is considered the simplified version because it doesn't have any radicals in the denominator. Now, if you look at part B, this is a problem for a different reason than part A was a problem, right? The reason part B is a problem is because you have a fraction inside of a radical, and we don't tend to like that. So here's how we deal with this. First of all, we apply the quotient rule. And then we rationalize, right? So we're going to multiply by something that'll force this radicand to be a perfect cube. Okay, we want it to be a perfect cube this time, not a perfect square like part A, because our index is 3, right? So we want this stuff to be a perfect cube. So we can sit here and think about that a little bit. 4 is already 2 times 2. So if I multiply it by a third 2, then I'm going to get 8, which is a perfect cube, right? So I'm going to multiply by a cube root of 2, and then b to the 4th. I need to force this exponent to be a multiple of 3, right? So that when I divide by 3, I don't have any leftovers. So the closest one is going to be 6, and I'll get to 6 by multiplying by b squared. Okay, so I think this is the winner. So we've got cube root of 2ab squared divided by cube root of 8b to the 6th. That's a cube root of 2ab squared divided by cube root of 8 is 2, cube root of b to the 6th is b squared. Now here I should pause to warn you okay? Because I said when we were doing part A that you could always just multiply by this same number to rationalize. That's true when you have square roots. It's not true when you have cube roots. Like if I had multiplied by the cube root of 4b to the fourth, I wouldn't have gotten a nice perfect cube. Watch. Cube root of 4b to the fourth times cube root of 4b to the fourth is equal to the cube root of 16b to the eighth. Problem is that 16 is not a perfect cube and 8 is not a multiple of 3. So multiplying by this exact same thing wouldn't have really done anything for us. Okay, so you really do have to think about, what do I need to multiply this number by to get a perfect cube, in this case 2, and then what do I have to multiply this variable by in order to get a multiple of the index. In this case, I needed to get to 6, and so I needed to multiply by b squared. Okay, so that's all well and good. That's how we take care of these situations when you just have a single term in the denominator. But what if you have two terms in the denominator? What do you do about something like part C? Well, if you think back to your algebra days, then you might remember something about multiplying by the conjugate, right? That's what you want to do here. The conjugate of a binomial is just the same binomial, but with the sign in the middle changed. So the conjugate of root 3 plus 2 is root 3 minus 2. And the thing about multiplying by the conjugate is that when you multiply by the conjugate, the middle terms cancel. And you can see this when you look at the formula for the difference of squares, right? If you're thinking about factoring a difference of squares, you know, a squared minus b squared is a plus b times a minus b, right? So you multiply a plus b times its conjugate, a minus b, and you don't end up with this trinomial, you just end up with a binomial, right? A squared minus b squared. And that's what we're going to get here too. So I'm going to multiply by the conjugate. Of course, I have to do the same thing in the numerator then. And we get 5 root 3 minus 10 over root 3 times root 3 is root 9. Then we have a negative 2 root 3. Then we have a positive 2 root 3. And then we have a negative 4. We have 5 root 3 minus 10 over square root of 9. Negative 2 root 3, positive 2 root 3 cancel. Minus 4. This is 5 root 3 minus 10 over negative 1, or in other words, we could call it negative 5 root 3 plus 10, or if you like, you could rearrange the terms and call it 10 minus 5 root 3. Either way, right? It's the same answer. So that's how we do that. Okay, hopefully that's not terribly unfamiliar to you. So that's how we divide with radicals. So we know how to multiply, add, subtract, divide. Right? So we can do all of this stuff with radicals. We can simplify them, right? On the first page, right? The number I showed up here, and we've seen the number I before back in chapter 1 when we were talking about the different sets of numbers and we got to the complex numbers. So let's hash this out in a little more detail, okay? I, as we've said before, is the square root of negative 1. Consequently, when we're working with complex numbers, right, when we're working with numbers like a plus bi, complex numbers, it's really the same thing as working with radicals. If you know how to work with radicals, then you know how to work with complex numbers, okay? One thing that I'll warn you of is that before performing any arithmetic with complex numbers, it's best to change the negative radicands to positive radicands by taking out the I, right? So if you have square root of negative a, you can rewrite that as square root of negative 1 times square root of a, and then square root of negative 1 is I, right? So you can rewrite it as I times the square root of a. And usually I'm not going to do this middle step. I'm just going to skip from here to here. Anytime I see a negative, if I have an index of 2, then anytime I see a negative radicand, I'm just going to rewrite it as I times the square root of the positive version. For example, square root of 25 I'm going to write that as I times the square root of positive 25. The square root of positive 25 is 5, right? So this is just 5I. In fact, most of the time I'm just going to skip from here to here. And in part B, well, 8, right? First of all, I can take out the I. And second of all, 8 is 4 times 2, and the square root of 4 is 2. So 8 is really 2 root 2. So I'm going to call this 2I times the square root of 2. I'll be honest with you. So this is the way that we usually write it in algebra textbooks and stuff. I don't like it like this. I would rather see it like this. I would rather see it as 2 root 2 times the square root of I. Because then that tells you this is the real part of the number, right? This is the coefficient, I guess you could say, on your I. It just makes it a little bit more clear to me. The reason that they don't write it like this is that sometimes it's a little bit ambiguous as to whether or not the I belongs underneath the radicand with the 2. But if you just put parentheses there, it's super clear. I kind of like this notation the best. But if you do it the top way, right, you're not going to be marked down. In fact, I think the solutions are probably presented this way. Okay, let's practice. Root negative 6 times root negative 30. Now remember my warning, right? You shouldn't perform any arithmetic until you've already rewritten the negative radicand as a positive radicand. Okay, so, and I'll show you why, but let's do it the correct way first, and then I'll show you the incorrect way. All right, so the correct way to do this would be to say this is I times the square root of 6 times I times the square root of 30. I times I is I squared. Root 6 times root 30 is root 180. Okay, 180. Well, there's got to be a perfect square that goes into that. 9 for sure. Is there anything bigger? Yeah, there's got to be 9. So 36, I think, goes into 180. Let's see. 180 divided by 36. Yeah, it goes in 5 times. 180. So this is 36 times 5. So first of all, I squared is -1, right? If I is the square root of -1, then I squared is just -1 itself. And then square root of 180 is 36 times 5. Square root of 36 is 6, right? So we get -6 root 5. That's our final answer. If we didn't rewrite it, if we didn't take out the i's first, we would have gotten this. -6 times -30 is positive 180. And then positive 180, as we've seen, is 6 root 5. So we would have gotten a positive 6 root 5 instead of the -6 root 5 that we should have gotten. Right? So this is the wrong way to do it. This is the correct way to do it. Right? So take out the I first. Let's do another one. So here we're subtracting a couple of complex numbers. And again, right, if you know how to work with radicals, then you know how to work with complex numbers. We work with radicals the same way that we work with variables. So really you can just think of I like a variable, like an x or something. You're going to combine like terms here, right? 6 minus 3 is 3. Negative 2i minus 3i is negative 5i. And that's all there is to it. If you want to multiply two complex numbers, well, then you FOIL, right? You FOIL. So we would get 2 times 7, 14. 2 times negative 3i is negative 6i. I times 7 is 7i. And I times negative 3i is negative 3i squared. That's 14 plus I minus 3 times negative 1. So that's really 14 plus 3, right? So that's 17 plus I. Okay. And then finally, if you're confronted with this kind of situation where you're dividing two complex numbers, then just like we did when we had radicals, we multiplied by the conjugate. Now we're going to multiply by the conjugate again. So conjugate of 1 minus 2i is 1 plus 2i. right? You just change the sign in the middle. This is going to clear the radical. So you'll see why. Or not the radical, but the complex number, the imaginary unit, I. So the numerator, if we FOIL this, we're going to get 6 plus 12i minus 2i minus 4i squared. In the denominator, we're going to have 1 plus 2i minus 2i. So those are going to cancel. Minus 2i, or sorry, minus 4i squared. So that's 6. 12i minus 2i is 10i. And then negative 4i squared is going to be a plus 4, right? Because I squared is just negative 1. So that negative and that negative will cancel and give us a positive. In the denominator, we're going to have 1, 2i minus 2i cancel, and then plus 4. So we're left with 10 plus 10i divided by 5, and that'll reduce, right? If you like, you can rewrite it like this, and then you see that each fraction reduces to 2. This is 2 plus 2i. Okay, so that's how division works with complex numbers, right? Really, it's the same as addition, subtraction, multiplication, and division of radicals. Okay. Now, the other connection that I want to make in this section is how radicals are really the same thing as exponents. Okay. Here's how this works. Excuse me. So we already know how to deal with negative exponents, right? We talked about that back in like 2.2 or 2.1 or something like that. 2.2, I think. We talked about negative exponents, right? Here's how we deal with fractional exponents. So here's how we deal with rational exponents, okay? So if you've got two natural numbers, m and n, remember that means they're positive whole numbers. So two positive whole numbers and a real number a, then a to the m over n is just the same thing as the nth root of a to the nth power. This definition may seem a little bit strange at first, but it's perfectly consistent with what we already know about exponents, and I'll give you a couple of examples to help you see that, right? So first of all, so 5 halves, 2 goes into 5 twice with 1 left over, so 5 halves is 2.5, right? So since 2.5 is between 2 and 3, we would expect for 4 squared, or sorry, we would expect for 4 to the 5 halves to be somewhere between 4 squared and 4 cubed, right? Well, 4 squared is 16, 4 cubed is 64, and 4 to the 5 over 2, based on this definition, would be the square root of 4 to the 5th power. Square root of 4 is 2, and 2 to the 5th power is 32. Sure enough, you get a number right in between 16 and 64. Okay, so that checks out. Maybe even more convincing is this. By the properties of exponents that we discussed, not in 3.2, we talked about that in, I think, 2.2. So by the properties of exponents discussed in 2.2, it should be the case that 8 to the 2/3 cubed is the same thing as 8 squared, right? Since you can just multiply these two exponents. 2/3 times 3 is 2, which is 8 squared is 64, right? Now, on the other hand, using this definition, 8 to the 2/3 would be the cube root of 8 squared. Cube root of 8 is 2. 2 squared is 4. So 8 to the 2/3 cubed is 4 cubed, and 4 cubed is 64, just like we would have expected, right? So this definition really ties in neatly with what we already know about exponents, okay? Let's practice a little bit. I'll give you a second to work on these 5. Okay, here's my solution. 4 squared is 16. 4 to the negative 2 is 1 over 16, right? That's how we take care of negative exponents, is we flip the number over, right? 4 to the 1/2. Now, that would be the square root of 4, right? Index 2, the denominator is the index, the numerator is the exponent, so this is 2 and then a 1, right? So it's just the square root of 4. That's just equal to 2. So what should 4 to the negative 1/2 be? Well, if negative exponents flip numbers over, and if 4 to the positive 1/2 is 2, then 4 to the negative 1/2 should be 1/2, right? Or maybe if you need to see the middle steps, what you could say is this. It's equal to 1/4 to the positive 1/2. That's 1/4, 1 over square root of 4, which is 1/2, right? Okay, 4 to the 3/2. Okay, again, remember, the denominator is the index of the radical. Since the index in this case is a 2, we don't write it. And then the numerator is the exponent. Also remember that you can do this in any order you want. So you can do 4 cubed first and then take the square root, or you can take the square root first and then cube it. That's what I'm going to do. I'm going to say this is 2 cubed, right? Because I'm really thinking of it like this, right? So square root of 4 is 2, 2 cubed is 8. So 4 to the 3/2 is 8. The reason that we bring this up, the reason that we talk about the fact that radicals are really just the same thing as exponents, is because it allows us to use rules of exponents to simplify radical expressions in a way that's maybe a little bit more clear. For example, we know that if you have the same index, right, nth root of a times nth root of, let's say nth root of a to the k times nth root of a to the l. This would be nth root of a to the k plus l, right? No big deal. But what if the indices don't match, right? Here we have an index 2 and an index 3, and we're trying to multiply these together. It's not clear how to do that when you're dealing with radical notation, but you can rewrite these. Square root of a is the same thing as a to the 1/2 power. Cube root of a is the same thing as a to the 1/3 power. So square root of a times cube root of a is really the same thing as it's really the same thing as a to the 1/2 times a to the 1/3. And we know how to deal with that, right? A to the 1/2 times a to the 1/3 is just a to the 1/2 plus 1/3. So you would add those two fractions together. You've got to get common denominators and stuff, but what you'll end up with is a to the 5/6. So there you go, right? Square root of a times cube root of a is the 6th root of a to the 5th. Kind of weird, I guess, but that's how it works. That's how it works out. Okay, and it's much easier to do that if you just are dealing with exponential notation instead of radical notation. So that's why we like to think of radicals as exponents oftentimes. Let's practice simplifying a couple things. So we've got 4x to the 1/2 times 3x to the 1/5. Well, 4 times 3 is 12. And then, so we're going to have 12x to the 1/2 plus 1/5. Right? We add the exponents. So let's do some scratch work, right? 1/2 is the same thing as 5/10. And 1/5 is the same thing as 2/10. So this is 7/10. So x to the 1/2 plus 1/5, that's going to be 12x to the 7/10. And I'm going to leave my answer in exponential notation because what I started out with was in exponential notation. So typically, we like to give our answers so that they match what we started with. If we start in radical notation, we want the answer in radical notation. If we start in exponential notation, then we want the answer in exponential notation. Let's do another one. 25x to the negative 1/4 divided by 5x to the 1/3. Well, 25 divided by 5 is 5. So this is going to be 5x to the negative 1/4 minus 1/3. Right? We subtract the exponents since we're dividing here. Negative 1/2 minus 1/3. That's going to be 5x to the common denominator is 12, right? And I get 12 by multiplying this one by 3, so I have negative 3/12 minus this one by 4/12. That's going to be 5x to the negative 7/12. Now, we don't really like the negative exponent business, so we're going to put that into the denominator. Just remember that it's only being applied to the x, it's not being applied to the 5. So the 5 stays in the numerator, the x goes down to the denominator where the exponent can be positive, right? So that's the final answer on part B. On part C, remember that you can distribute exponents across multiplication. So I can think of this as 32 to the negative 1/5 times x to the 2/3 times negative 1/5. That's negative 2/15. Right? So this is going to be 1 over 32 to the positive 1/5 times x to the positive 2/15. 32 to the 1/5 power, that's the 5th root of 32. So we're thinking what number times itself 5 times gives us 32. And I think 2 does the trick, right? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, right? So 5 times 2 multiplied by itself 5 times gives you 32. So definitely this is 1 over 2x to the 2/15. Okay. And that's that one. Let's talk about factoring. Before we do, now these things look so scary, don't they? You're looking at this, you're probably thinking, factoring, how in the world are you going to factor that? But remember, when we briefly covered factoring in, I think it was 2.2, we talked about the fact that when you're dealing with, when you're dealing with the coefficients, you can always take out the LCD. When you're dealing with variables, you can always take out the variable that has the smallest exponent on it, right? So looking at part A, for example, I have a factor of x here. So this is a two-term thing, right? Here's one term, and here's another term, okay? On this first term, I have an x as a factor, but I don't have an x as a factor in the second term, so I can't factor out any x's. But I also have an x plus 1 as a factor in the first term, and I have an x plus 1 in the factor as a factor in the second term as well. That tells me that I can take out an x plus 1. How many of the x plus 1s can I take out? I can take out the smallest exponent of them. So the smallest exponent in this case is going to be negative 1/2. So I can factor out an x plus 1 to the negative 1/2, and then to see what's left over, we divide each of these terms by the factor that we factored out. So doing a little bit of scratch work, right? X times x plus 1 to the negative 1/2 divided by x plus 1 to the negative 1/2. Well, that's easy. That's just x, right? So for the first term, I'm just left with x. For the second term, 2 times x plus 1 to the positive 1/2 divided by x plus 1 to the negative 1/2. Well, I would subtract, right? I would do 1/2 minus negative 1/2. That's 1/2 plus 1/2, which is 1. So this is going to be 2 times x plus 1 to the first power, or in other words, it would just be 2 times x plus 1. So I can continue to simplify this now. This is going to be x plus 1 to the negative 1/2 times x plus 2x plus 2. So that's x plus 1 to the negative 1/2 times 3x plus 2. And there we go. That's how you would factor these things. Okay, I'll let you look at part B. Go ahead and give the video a pause and see if you can do part B on your own. Okay, here's my solution. I have a 4/3. I'm not going to have any LCDs that I can factor out. I have an x term or an x factor here and an x factor there. That tells me I can take out an x. I can take out an x to the lowest exponent, which in this case is 1/3. And then I have another term of x plus 5 in the first term, but not in the second term, so I think that's as far as that one's going to go. So this is going to be x to the 1/3 times, what are we going to be left with? If we divide by x to the 1/3, we're going to be left with 4/3 times x plus 5 for the first term. And for the second term, I'm going to have x to the 4/3 divided by x to the 1/3. That's x to the 4/3 minus 1/3. That's x to the 3/3, which is just x to the first power, or in other words, just x. Okay, so I've got x to the 1/3 times 4/3 x plus 20/3 plus x. 4/3 x plus 1x. 1 is the same thing as 3/3, right? So 4/3 x plus 3/3 x is 7/3 x plus 20/3. It might be kind of nice to pull out the 1/3. I mean, this answer is fine, but I'm going to pull out the 1/3. Call this 1/3 x to the 1/3 times 7x plus 20. That, I don't know, that just looks a little bit nicer to me. Okay, but that's the answer there. One more. Again, go ahead and put the video on pause. See if you can factor this one. Okay, looking at these three terms, there are three terms now, right? There, and there. So looking at those three terms, the one factor that they all have in common is 2x plus 1. And the smallest exponent is -3/2. So I know I can take out a 2x plus 1 to the -3/2. What am I going to be left with? Well, for the first term, I'm going to be left with x minus 2. For the second term, I'm going to be left with 2x times 2x plus 1 to the what? Well, -1/2 minus -3/2. That's -1/2 plus 3/2. That's 2/2, right? Which is 1. And then in the last term, I'm going to be left with a negative sign. I'm going to be left with a 3. I'm going to be left with a 2x plus 1 to what power? 1/2 minus -3/2. That's 1/2 plus 3/2. That's 4/2, which is 2. Okay, so I get 2x plus 1 to the -3/2. Let's see. So this is going to be times x minus 2 plus 4x squared plus 2x minus 3 times 4x squared plus 2x plus 2x is 4x plus 1. So let's see. X minus 2 plus 4x squared plus 2x minus 12x squared minus 12x minus 3. Now let's combine some like terms and write in descending order. So x squared's first. I've got 4x squared minus 12x squared. That's -8x squared. Then x's. I've got x plus 2x, that's 3x. 3x minus 12x is -9x. So I've gotten rid of these things so far. And then I've got a -2 minus 3, that's -5. I suppose it wouldn't hurt to take out the negative sign. That might make it a little prettier anyway. So we take out the negative, got -2x plus 1 to the -3/2 times 8x squared plus 9x plus 5. Okay, and there's the factorization of that. Oh man, maybe we could factor this further, right? Maybe we could factor this trinomial. Should we try? Yeah, I think we can, right? Seems like we could do, oh, maybe not 8x, maybe maybe 4x plus 5 times x plus 1. Oh, it would have to be 2x though, wouldn't it? Shoot, I was thinking 9 that way, but this would have to be 2x in order to get an 8 there. Maybe this doesn't factor. Actually, I don't think that does. Now that I'm looking at it a little more closely, I don't think that factors. So that would be our factorization there. Okay, so that's how factoring works with these things. One last thing that I just want to mention briefly is what we've seen about even roots of negative numbers, right? So we've seen that square roots of negative numbers are just complex numbers, but what about 4th roots or 8th roots or 6th roots or 12th roots or whatever? Like, what's the 4th root of -1? It can't be -1, it can't be +1, obviously. It also can't be I, right? I to the 4th power is +1. So what is it, right? How do you get the 4th root of -1? Well, should we invent a new number? Like, should we invent j or something and say j is the 4th root of -1? Well, it turns out that that's not necessary. It turns out that this is a complex number. We can rewrite this in the form a plus bi for some real numbers a and b. In fact, to be specific, I think it's something like √2/2 plus √2/2i. That's one of the 4th roots of -1. There are 3 others. We're going to talk about this concept in detail later on in this semester. But for now, what I want you to understand is that the 4th root of -1 is not undefined. It's defined, right? There is a 4th root of -1. It's just not a real number, right? It's a complex number. Whereas something like 2/0, now that is undefined. That's nonsense, right? 2/0 is just straight nonsense. Okay, so that's it for this section.